Good afternoon everyone, welcome to the channel. Today I will show you how to make an autoencoder model in using PyTorch. I am using Jupyter Notebook, so let's get started. So at first I want to import some libraries. Let's import torch, from torch import nn_optim, from torch details.data import data loader, torch vision, from torch vision import that's a mistake, datasets transforms, from torch info import sum, numpy as np, matplotlib.pyplot as plt. Okay, these are all the required libraries that we need. Now define the device. I like to write some useless codes in this particular cell block all the time. So let's check the PyTorch version. Torch.version. Let's check the GPU name that we have available. Torch CUDA get device name. Now the important line that matters. Torch CUDA is available else CP. So let's check our device. Another line that I would like to add is total number of GPUs. Torch CUDA device count. Okay, I want to add some new lines so that it's easier to see. Okay, our PyTorch version is 1.12.0 and we have GPU available, this GPU, and total number of GPUs is 1. Now time to load USPS dataset. Okay, train dataset, datasets.USPS. So in my current directory I want to save my dataset in this folder, data source. Is true, download true, drop last, also true. copy this line for the test dataset as well. Test dataset, we have to mention train is equal to false in case of test dataset. Sorry. This is not transforms. Okay, so our dataset have been downloaded. Let's check the length. So there are 7,291 samples in our trained dataset and 2007 samples in our test dataset. Okay, let's visualize one of them. So we are going to use matplotlib for visualizing one of the trained samples. Okay, let's use 𝒐𝒂𝒅 title train targets axis train dataset target 0. Oh, sorry, not this bracket, this one. Oh, so many mistakes in one figure, on cell box, sorry. Okay, so we have visualized one of the samples. Okay, now we have to define the data loader. Let's define data loaders. So train data loader. So we have to pass our train dataset. Batch size, let's say 32. Shuffle true for train dataset. Broadcast is also true. Now copy this one. We have to also define the data loader for this dataset. And we don't need to shuffle the test dataset. Sorry, test dataset. Okay, now it's time to define the network architecture. So this is how we can create an AutoEncoder model using PyTorch. So we have to create an AutoEncoder class. This is the constructor. Okay, now we need to sequentially add the encoder layers. Let's write nn.spatial. Now we are gonna sequentially add the layers to this nn.encoder. So let's give it a name, and dot linear in features 16:16. Okay, I forgot to mention the yes, so this case, so print in dataset data shape. You can also use it for test. So the spatial size of USPS digit images are 16:16. So that's why we mentioned 16:16 in this case. Okay, out features. Let's say out features we will calculate 128. Now we are gonna add a ReLU layer and ReLU true. Now I want to copy this to paste to. Now in this case the in features will match the out features of the first linear layer, and we have to change it, let's say 64. Then I want to add another linear layer. Okay, this will also match the out features of this previous linear layer, 64, and let's say 40. Okay, this is our encoder block. Now we have to write decoder block as well, and enter sequential. Now sequentially we're gonna add the layers in the decoder. So let's select in features 40. This will match the previous out features. Now we are gonna do the inverse operation. So we have reduced it, and now we are gonna increase it again. 64 self decoder add module value 3 and dot value true. Okay, now copy these two lines. Okay, change to 2. This will be 64. Let's take it to 128. And finally, I want to use another linear layer. So this is 1 and 128 to 16:16. Original image shape. So this is just my choice to write it 3 then 2 then. It's not necessary, because this is going in inverse direction. That's why I like to use the opposite order. Now we have to define a forward method. Okay, x below on. After changing the shape of the x, this is flattening the input size. We're passing it to encoder then we are passing it to decoder. Finally, we have to change the shape of the input again. We have to make the notation like batch size, channel, height and width again, because in this case the flattening factors will be operated by the model. Then after operation is completed, we have to convert it to the PyTorch tensor shape again. Okay, return X. Now let's visualize the model architecture that we just created. Visualize the model architecture. Okay, so let's first create model A, and we have to send it to GPU. Input size. So our batch size is 32, and this is the number of channels is 1 because these are grayscale images. These are all grayscale images. Let's say 16. Sorry. Quite an stupidity. Okay, so this is our model architecture. So this is the operations that's taking place in the encoder. So this is the batch size, and this is how features are changing, and this is the bottleneck 40, and again reverse operation is happening in the decoder. Now we have to create a train batch. So in case of training, we have to write model.train. We have to move the data to the GPU. Then calculate the output, then also calculate the loss. We have to first give the prediction by the model, then we have to give the actual data. Then 3 common steps. We have to first write optimizer 0 pat, then loss backward, then we have to write optimizer step. So this line calculates the gradients and this line updates the weights, and we don't want to accumulate the gradients, that's why we have to write this line as well. This will flush out the previous calculated gradients. Now return loss. Similarly, we will write a test batch as well. Sorry, with torch dot inference mode. Test batch data model criterion. So we are not going to train the model using these samples. We are going to just see how the model is performing on these test samples. So in this case, we have to write model.eval. Again, move the data to GPU. Then calculate the output. This is the prediction that model gives. Then get loss. We don't need to write any optimizer code in this part. So loss is criterion. This is the model prediction and this is the original data. Then return loss. Okay, now we have to set up model criterion and optimizer before training. So let's create a model instance and send it to GPU. We are going to use mean squared error as our loss function. This is dot. Okay, so now optimized. Optim dot add-on. So AE dot parameters and learning rate. Let's select 0.001. Now it's time to train the model. So first we have to select random seed. Let's use 42. Now we are going to train the model for 100 epochs. Train loss, test loss. Now we created two empty list for epoch in range n epochs. Create two more lists, train losses, test losses. Okay, for data, train data loader. We don't care about the labels because this is not supervised learning task. We don't need the labels. So trn batch loss, train batch. We are calling the train batch function that we wrote here. Train batch. Let's provide our data model criterion optimizer. Okay, so now we are going to append per batch losses into a list. So train loss adjustment batch loss item per batch loss. So train per epoch loss. Sorry, per epoch loss. We're going to convert the losses that is accumulated in this list into a numpy array. Train losses, then calculate the mean of this. Okay, the same thing we have to do for the test dataset as well. So we are gonna write test data loader. This is test batch loss. We don't need optimizer in this case, and we have to call the test batch, then test losses, again test batch loss item, test per epoch loss, test. So we have replaced all the trains with test, and we don't need optimizer because we're just going to observe model performance on this data while training. The model do not learn anything from this data. Now train loss that happened, train per epoch loss, same with test. Test per epoch loss. Now we do not want to print everything, so we only want to print after the result, model results after every 10 epochs. So if epoch plus 1 remainder 10 equal to 0, then only we want to print the model results. So let's epoch. And n epochs. N epochs is fixed. We were training the model for 100 epochs. Okay. Then let's put a tab. And we want to observe the train loss as well. Train loss will be train per epoch loss 14F. Okay, and so and print test lost test per loss 14F. Okay, I think that's enough. Now let's start the training. Okay, so we have written a training loop, and this will take some time. So after 10 epochs, the train loss is 0.00 something. Test loss is a little bit higher, and gradually it is decreasing. So let's wait for some moment till the training is finished. Okay, we are towards the end almost, and you can see the losses are decreasing with in number of increasing epochs. So now let's plot the model loss. Okay, so plt.rc font size to within quotation. Okay, let's select 18. plt.figure fig size, let's select this figure. Okay, and then plot plt.plot train loss, give it a red color, give it a label as well. So this is train loss. plt.plot test loss, let's give it blue color, label test loss. Okay, now we want to just give a title loss curve, level we have the number of epochs in x level, and y level we have matrix dot legend. Okay, so this is our model loss. So I hope I can show you within. Okay, so this is the loss curve. We can see both are gradually decreasing with time, with the increasing number of epochs. Okay, now let's make a prediction. I have to give a number 12 here. Okay. Let's first create a list. So for a range, this data set. Let's append 5 samples in this list. Also, to select it here, not here. This is 5 samples. Figure on axis on dot subplots on 5 pixels 7 2 for I in range 5. Sorry, x I am show. gi dot squeeze 𝒐𝒓𝒃𝒄𝒉 dot set xticks. We're gonna remove all the values from the x-axis and all the values from the y-axis as well. Okay, and finally figure on. Here we have a title original. Increase the font size 20. Okay, now we have to compare it with model performance as well. So REC, reconstruction, for the range 5. REC dot append. This is our model. We have to take it out from the GPU to CPU and then provide the original images one by one. Okay, here to axis to build of subplots 5 size 7 2. Now I can just copy okay, not now, or say in range 5 x2 dot j and show this j squeeze CPU detach dot numpy. Sorry, I have to put bracket here as well. So this is converting tensor to numpy array. Snap gray. Now I can copy this. So remove tool with J and figure on figure 2, and this is reconstruction, not original. Reconstruction. Okay, consistent. Let's see this. Okay, put a semicolon. Okay, so this is our model performance. Now very difficult to understand, but you can see just in this area these are little bit blurry and quite difficult to understand because these images are have a very low resolution, but these are the prediction after 100 epochs given by our model, and these are the original first 5 datasets available in the test samples. Okay, so in the next video I will repeat this task using a convolutional autoencoder instead of just autoencoder. So here we have used linear layer, but in convolutional autoencoder we have to replace them with convolutional layers, and we also want to see how our model performs. So this is it for this video. If you like this video, please subscribe to the channel. Thank you.